This is Chapter 5, Integrals Part 1, Section 5.1, Area and Distance. It is important in many applications to find the area under a curve. In this section, we will discuss methods used to approximate the area under the curve of the function and above the x-axis and between two given values. So the idea here is that we are going to take this curve and we're going to go between two values. We'll say A here and B down here. And if you notice, my graph of my curve is above the x-axis for this whole entire region between A and B. And I'm going to split this into rectangles. So I'm going to try to make them equal width when we do this. And we're going to go ahead and have rectangles and drawing up and making rectangles from each of these values. If you notice from this, we have an approximation here. I'll say this is B. And we can easily find the area of each of these rectangles. And if you notice, it's not exact, but it is a pretty good approximation. And there's better ways to make this more exact. One of them would be to, instead of having 4 rectangles here, what if I were to have 8 rectangles? Or 20 rectangles? Or 100 rectangles? Or if you see the idea of this, so we're taking a limit as n goes off to infinity, so the number of rectangles gets infinitely large. So the next part says, suppose that the graph below represents the velocity v of t of a car in miles per hour after t hours. Find the shaded area and what does it represent? So from algebra, we know that distance equals rate times time. And we know that from recently what we've been talking about, rate, how fast something's moving, is the same thing as the idea of velocity. So if you notice here, I have the area, and to find the area of anything, and if you wanted to split this easily into a rectangle and into a triangle, let's just talk about the rectangle here. If you had that, there's 2 units times the height, which looks like about 15, and we'll say this is 30. Now what units are going to go with this if you did miles per hour times hours? Well, the hours would cancel out and you'd be left over with 30 miles. And then likewise for the triangle, triangles are going to be 1/2 base, which is 2 units. And our height, which is about, looks like 10. And then going ahead and multiply this out, we get 10 miles. So total, this car drove 40 miles. So next, right below this is, so there's a lot of applications in this, just so we're aware of that, and we will extend upon this idea too. And then this also is the idea that gets built upon in Calculus 2. So we have an example here. It says, given y equals x squared plus 3 on the interval from 0 to 2. Suppose we want to find the area under the curve. This problem says, use 2 rectangles of equal width. Okay, so equal width, with height defined by the left endpoint, or L2. And then there's another example next to this, which says now using 4 rectangles equal width defined by the right endpoint, or R4. If you notice, they use an L because it's left, and the little 2 is because there's 2 rectangles, and R because it's the right endpoints, and a little 4 because there's 4 rectangles. So I have a curve here, and we're defining this on the interval from 0 to 2. Tells us that in the problem. So there's 0 and there's 2. So I need to split this into 2 rectangles, and if I do that, it's going to divide my rectangle at 1. So from 0 to 1, and then from 1 to 2. And it says to use the left endpoints. So I'm going to take on the left side starting at 0 and go all the way up to my graph to where it touches. And then once I hit the graph, I'm going to draw a horizontal line across and then straight back down to 1. Okay, and then I'm going to make my second rectangle, taking at 1, going straight up until I touch that graph, and going across, and then back down at 2. Okay, and because these are rectangles, the area is very easy to find. So if you look at the first rectangle, we have a height of 3, and a base of 1, so this works out to being 3 units. And then the next one is going to be the height looks like 4, and that base is 1, so we get 4. And so total area here would have been 3 plus 4, which is 7. And we're going to go ahead and put down units squared. So for the next example, it says use 4 rectangles equal width, and this time we're going to define the right endpoints. So again, we're still going from 0 to 2. So think about how we can split this domain from 0 to 2, this interval, into 4 equally spaced rectangles. And again, we're going to go from the right endpoints. We will finish this up together. On page 2 of section 5.1, at the top of the page it says, when the heights of the rectangles are determined by the minimum function values on each subinterval, our area estimation is going to be a lower sum, and it is always under the true area of the curve. When the height of the rectangles are determined by the maximum function values on each subinterval, our area estimation is an upper sum, and it is always over the true area of the curve. We have another method to use besides just left endpoints and right endpoints. The next one's going to be midpoints, which is going to be a better approximation than the other two that we've seen so far. And for this problem, it says, again, using 4 rectangles, equal width. And this time the heights are defined by the midpoints. And if you notice, we have M sub 4. M meaning midpoints, and 4 because there are 4 rectangles. So we'll talk about this one. If you have your interval and cutting this into 4 pieces, that base of those rectangles is going to be by 0.5. And for this, we're going to make sure that when we draw our rectangles, we are using that midpoint. So in between 0 and 0.5 is 0.25. So you're going to draw a vertical line up until you touch the graph, and then draw a horizontal line across, and then back down to make the sides of the rectangles. Likewise, between 0.5 and 1, your midpoint would be 0.75, so drawing a vertical line up until you touch that graph, and then a horizontal line across and coming back down to define that rectangle. The next one that we have in between 1 and 1.5 is going to be 1.25, so again, drawing a line up until you touch that graph, a horizontal line across, and then back down to our values. So this is our third rectangle in here, and our first one, and then we'll go ahead and do our second, and then our fourth rectangle in between 1.5 and 1.5 and 2 is 1.75. So again, drawing a vertical line up until you touch your graph, and then a horizontal line across through that point, and then straight back down. And then this is going to define our fourth rectangle. This is the best approximation method to use to find the area underneath the curve. So our area for the first rectangle that we have, that base is 0.5 or 1/2, whereas 0.5 times, and how do you figure out the height of this rectangle? In order to figure out the height of this rectangle, and again, the rectangle is defined by this function y equals x squared plus 3, we need to substitute in x is 2.5. So I need to find f of 0.25, which is going to be 2.25 squared plus 3. And I'm going to write that as a fraction. You can easily do that on your calculator, but that works out to being 49/16 plus the next value to find. We have f of 0.75, and so we have 0.75 squared plus 3. That's the height of that rectangle. So our base of the rectangle is 0.5, and the height of the rectangle is going to work out to being 57/16. Plus the next rectangle that we have, that midpoint that we substitute in was 1.25. So we have 1.25 squared plus 3. And so the base of the rectangle is 0.5 times the height, which works out to being 73/16, plus, and then our last rectangle, that base again is 0.5, and substituting in 1.75 into my function and squaring it and then adding 3 works out to be 97 over 16. Working this all out, just plugging that in on your calculator, we get 69 over 8 units squared, or it's approximately equal to 8.625 units squared. So we have a left endpoint method, a right endpoint method, and a midpoint method. So terminology, we have A is the left endpoint of the interval, B is the right endpoint of the interval, capital N is the number of subintervals that we have, and delta x is subtracting those two, your upper bound minus your lower bound, and dividing by the number of intervals that you would like to have, or the number of rectangles. So we have, by definition, we worked these all out. You'll notice that we have 3 different definitions on here. The first one is going to be the nth left endpoint approximation. And so I'll take some time to look that over. And then we have the nth right endpoint approximation. And then the next one is the nth midpoint approximation. And we did an example of all of these. Notice that we do use L sub n, R sub n, and M sub n. There are some pictures to go along with this right below. And you'll notice that left endpoint, we have a right endpoint, and we have the middle, or the midpoint method. And you can also notice that when you have more rectangles, the better off approximation your area under that curve will be. It says in order to find the distance traveled during a certain time period, when we know the velocity in algebra, we could find the distance. If velocity is constant, we have distance equals velocity times time. For example, if we travel at 40 miles per hour for 2 hours, then distance, which is going to be our rate times time, is equal to 40 times 2, which is equal to 80 miles. If velocity is not constant, then there's no easy formula, so we can take sample readings of velocity at a lot of different time intervals and make estimations of the distance traveled on each time interval based upon our sample velocities. There's an example below that is an example of that idea. It says estimate the distance traveled given the following sample velocities. There is a table and then there's also a graph. Most of the time you see one either as a table or as a graph, usually not the same in one problem, but it allows you guys to see both of these and as we work this out. So we're going to have to figure out estimate the distance traveled. So distance is equal to rate times time, or velocity times time. And if you notice, our increments up here are counting by 5s. That's the width. You can also notice that that's down here too, that the